Okay, so welcome to this first video in the playlist on metabolism. In this video, what we're going to talk about is the structure of the aldoses. Okay, so monosaccharides can be broadly divided into two types, the aldoses and then also the ketoses. Now we're going to discuss the aldoses in this video, and then we'll have another video to discuss the ketoses. Right. Okay, so let's get on with it then. So basically, the aldoses are based on a molecule called glyceraldehyde. Okay, so this is why the aldoses are called the aldoses, because they're based on an aldehyde, basically, specifically this molecule glyceraldehyde. Okay, right, so there are two optical isomers of glyceraldehyde. Okay, so let me show you the two of them. So, firstly, let me start by drawing the structural formulae of glyceraldehyde, which I'll just draw in in a two-dimensional plane, and then I'll draw the three-dimensional structures and show you how there are two optical isomers of glyceraldehyde. Okay, so this is the structural formulae of glyceraldehyde. Okay, so here's the aldehyde group, and then what you have is a glycerol molecule, effectively. So a glycerol molecule is propane 1,2,3-triol, i.e. it's a 3-carbon molecule where you have an alcohol group off each of the carbons. Obviously, the difference between glycerol and glyceraldehyde is that this third carbon, instead of just having an alcohol group off, like this carbon over here, instead it's an aldehyde group. So this is the structure of glyceraldehyde. Now, you will notice that this carbon here, which I'm now circling in pink, this is a chiral center. It has 4 groups coming off it, which are different. Okay, so that means that there are 2 optical isomers of this molecule. Okay, so when you have a single chiral center, that gives rise to 2 optical isomers of the molecule. We don't have any more chiral centers. This certainly isn't a chiral center, and neither is this. Okay, so we have 1 chiral center, and therefore there are 2 optical isomers of this molecule. Okay, so let me show you the 2 optical isomers of this molecule, and now I'm going to move to drawing skeletal formulae rather than full molecular formulae like this. Okay, because it will take us, well, it's easier on the eyes. Firstly, skeletal formulae are easier on the eyes, and also they're quicker to draw. So, remember, in skeletal formulae you don't show carbon atoms, okay, but you show everything apart from carbon atoms and apart from hydrogens coming off carbon atoms. So carbon atoms are shown implicitly by corners. Okay, so here is this double bonds to the oxygen up here, and then we've got a carbon implicitly here at this corner, which is this carbon here, and then we don't show the hydrogen coming off this carbon because we don't show hydrogens coming off carbons. Then we'll have another corner over here, which will be this carbon here, okay, and it will have a hydrogen coming off and also an alcohol group. We don't need to show the hydrogen, but we do need to show the alcohol group, so I'll show this in a moment. And then you have an alcohol group coming off this final carbon here. Okay, and then the 2 hydrogens we just don't show. Right, now we need to take account of the optical isomerism here. Okay, so basically, imagine these 2 bonds are in the plane of the piece of paper. We then have to decide whether the hydrogen, well, we have to add on the hydrogen and the alcohol group. Now, we don't show the hydrogen, but the alcohol group can either be coming out of the page at us or going into the page away from us. So if the alcohol group is coming out of the page at us, then the hydrogen atom will be going into the page away from us. And if the alcohol group is going into the page away from us, then the hydrogen will be coming out of the page at us. Now those are the 2 optical isomers of this molecule, okay? So they are truly different molecules. You can't change one into the other without performing a chemical reaction. So let's firstly draw the one where the alcohol group here is coming out of the page at us. Okay, so the rest of the molecule that we've shown is in the plane of the page. And now this alcohol group is coming out of the page at us, and the hydrogen atom that comes off this carbon is going into the page away from us. Okay, so this is known as the D isomer of glyceraldehyde. So you would refer to this as D-glyceraldehyde. And it is very important that we discuss all of this because all of the later ones, like glucose and mannose, this D-glucose and D-mannose, it's all based on this same D system here. Okay, so it's very important that we discuss this so that we have a full understanding of where the names of the hexoses later come from. Okay, and then the other optical isomer of glyceraldehyde is like so. So I'll draw the same structure out again. So here's the 3 carbons here, and then we have the alcohol group coming off over here, and this time the alcohol group will be going into the page away from us, which I'll show by this dashed line here, and the hydrogen will be coming out of the page towards us. And this optical isomer of glyceraldehyde is known as the L isomer, so the whole molecule will be referred to as L-glyceraldehyde. Okay, so we have D-glyceraldehyde and L-glyceraldehyde, okay, and both of these molecules are known as the Aldo trioses. So they are aldoses, and specifically they're Aldo trioses because they have 3 carbons, so tri is for 3. Okay, so Aldo trioses. So they are considered monosaccharides, D-glyceraldehyde and L-glyceraldehyde. Now, the main one that is going to be within cells is D-glyceraldehyde, and the main, all the other aldoses that we're going to see are going to be based on D-glyceraldehyde. So in principle, you could build the L isomer of all the later aldoses that we're going to see, and these would be analogous to the L-glyceraldehyde that we see here, but in reality, cells don't use this isomer, basically. They use D. That's why you hear about D-glucose, D-mannose, and never about L-glucose and L-mannose. Even though L-glucose and L-mannose exist chemically, they're not important to life, it doesn't seem. Okay? So in biochemistry, we don't study them. However, for completeness, we will keep talking about the fact that there are the D and the L isomers of all of the aldoses. Okay, but the structures that we're going to draw from now on are going to all be about this D isomer, and that will become clear in a moment. Okay, so before we move on, I just want to show you the other way that people often draw these. These pictures are lovely because they actually give you a sense of the 3D structure, so they make it very nice and easy to visualize. However, they are time-consuming to draw. Even though they're skeletal formulae, it's still time-consuming to draw a 3D structure like this. So, the way people often denote these molecules is for a different way. So let me show the way people will usually draw these. The way you will usually see it, if you were to Google aldoses and get the Google images up, this is what you'll see basically. You'll see molecules that look like this. Okay, so you put this CHO here, and this doesn't mean Chinese hamster ovary cells, okay? Instead, it means the aldehyde group up here. So this refers to this aldehyde group. Now, to denote that the alcohol group of this second carbon is coming out of the page at us, what you put is an HCOH there. Okay, so putting the alcohol group on this side denotes that it's coming out of the page towards us if you were to draw a structure like this. Whereas if we want to show it going into the page for L-glyceraldehyde, again we'll show the CHO here, the aldehyde group, but this time we'll put HO and then CH to denote that the alcohol group is going back into the page away from us. Okay, so putting the alcohol group on this side of the structure denotes that it's going away into the page away from us. Putting it on this side denotes that it's coming out of the page towards us. So through these drawings, we are communicating the same amount of information as is in these drawings. Yes, this is closer to what the molecule actually looks like, but we can communicate the information in these simpler drawings. Okay, and then finally what you'll have is a CH2OH group there in both cases. So this is how people will often draw the 2 isomers of glyceraldehyde. The D isomer will be drawn with the alcohol group on this side to denote that it's coming out of the page towards us. If you draw the structure when you put the aldehyde group over here and this alcohol group, this far terminal alcohol group on this side, okay? the alcohol group will be coming out of the page towards us, and that's denoted by having it on this side, this right-hand side. And if you have the alcohol group on the left-hand side, it will denote that it's going into the page away from us. And this notation will become very useful when we go further, okay? So, now, let's discuss the aldo tetramers now. So these are all going to be based on these glyceraldehyde molecules. Now we will draw the D isomers of the aldo tetramers, but you can imagine what the L isomers would be. Okay, right. So, firstly, let's start with D-erythrose. Okay, so D-erythrose. So let me show you the structure of this, and then let me show you how it's based on D-glyceraldehyde. Okay, so here is the carbonyl group again, or the aldehyde group here. Okay, then you have the first carbon, the second carbon, the third carbon. Well, actually, no, this is the second carbon, this is the third carbon, this is the fourth carbon, because I've missed out this first one here. So the aldehyde carbon is always considered the first carbon. So first carbon, second carbon, third carbon, fourth carbon, and then off the fourth carbon you'll still have this alcohol group here. Now, off both of these carbons then, you now have alcohol groups. And off this carbon it's coming out of the page towards us. And off this carbon it's also coming out of the page towards us. So let me stress that both of these carbons are now chiral centers. Okay, so off this carbon you'll have an alcohol group coming out of the page towards us, and then a hydrogen going into the page away from us. Off this third carbon here you also have an alcohol group coming out of the page towards us, and then a hydrogen going into the page away from us. Now, this is based on glyceraldehyde because we've effectively added in another carbon in between this carbon and this carbon. So let me stress something. This carbon here, the carbon here, is this carbon here, not this carbon here. So what you've done effectively is you've added in another carbon in between this one and this one. Okay, so here's the new B, okay? And in D-erythrose, what you have is the alcohol group coming out of the page towards us. Now there is another D-aldo tetrose, okay? So this next one is what's known as D-threose. So D-threose. And this is the other optical isomer of this. So we're talking about the D isomer, so this alcohol group here always has to be coming out of the page, because this is this carbon here, remember, and the alcohol group was always coming out of the page when we talked about D-glyceraldehyde. If we were to draw L-erythrose, this alcohol group would be going into the page away from us, just like it is in L-glyceraldehyde. Okay, but as I said, we're going to concentrate on the D isomers always. If you want to change them to the L isomers, all you have to do is modify the carbon that's next to this carbon here. Okay, so that it's no longer coming out of the page towards us, but instead is going into the page away from us. So let's draw the structure of D-threose now. Okay, so again, here's the fourth carbon, here's the alcohol group, and because it's the D isomer, it's based on D-glyceraldehyde, so the alcohol group on this penultimate carbon, the carbon before the carbon which has this alcohol group here, is coming out of the page towards us. And now, the carbon off this second carbon, which remember is the new thing that we've added in, this now is going into the page away from us. Okay, and then you have the aldehyde group here. Okay, so these are the two aldo tetroses that you can make. Okay, and again, these are considered as monosaccharides. So aldo tetroses here, D-erythrose and D-threose. Okay, so you could also make L-erythrose and L-threose, and to make L-erythrose and L-threose, you would take the alcohol group on this carbon here, on this third carbon, and instead of having it coming out of the page towards us, we'd have it going away from us into the page. And the same if we wanted to create L-threose, we'd have the alcohol group going into the page away from us, and the hydrogen would come out of the page at us. Okay, so these are the two D isomers of erythrose and the D isomer of threose. Right, but there is also an L isomer of erythrose and L-threose. And you can see that D-erythrose and D-friose are optical isomers of one another. All that changes is whether the alcohol group of this second carbon is coming out of the page or into the page, basically. So, overall, there are 4 aldotetroses. There is D-erythrose, D-friose, L-erythrose, and L-friose. And that reflects the fact that there are 2 chiral centers, which each gives rise to 2 optical isomers. So 2 times 2 is 4. Okay, right. So, from D-glyceraldehyde, you get these 2. You get D-erythrose, and you get D-friose. Okay, right. So, now let's discuss the Aldo pentoses. Okay, so we're now going to add in another carbon, and we're going to add it in between this second carbon here and this first carbon. So again, we're going to break this bond, and we're going to stick in another carbon. Okay, and again, this is going to be a chiral center, so it can have alcohol groups either coming out of the page or into the page. So, now we're going to start with D-erythrose, okay, and we're going to add in this next alcohol group. Okay, so let me put this in. So let me draw the structure now, like so. Okay, so here's the carbonyl group. Let me just make sure this is in view. Okay, so here's the aldehyde group here. Now, this carbon here is now the equivalent carbon of this one. So we've based this molecule on D-erythrose, so the alcohol group of this carbon is still going to be coming out of the page towards us. And the alcohol group of this carbon, this carbon is now the analogous of this one. Okay, so this again is coming out of the page towards us, like so. And then this carbon is this carbon, and then of course off here you'll have the alcohol group, so that's not a carbon. Okay, now we've added in this new carbon. This new carbon is a chiral center, so it can either have the alcohol group coming out of the page towards us, or it can be going into the page away from us. So if it's coming out of the page towards us, which is the one we'll start with, you get a molecule which I'm sure you've all heard of, which is called D-ribose. Okay, so this is the molecule known as D-ribose. This is the linear version of ribose. The form of ribose that you use in RNA is the cyclized version of D-ribose. So we'll see that in a moment. Okay, so we'll talk about cyclization later once we've completed all the linear structures. Okay, so you can also make another molecule that's based on D-erythrose, where the alcohol group of this new carbon doesn't come out of the page, but instead goes into the page. Okay, so let's draw this structure now. And again, here's the carbonyl group here. The alcohol group of this second carbon goes into the page away from us, and then of this third carbon, it's coming out of the page towards us, because remember, it's based on this D-erythrose structure, where the alcohol group is coming out of the page towards us, and then of course it was based originally on D-glyceraldehyde, so this alcohol group then has to come out of the page towards us. Okay, this is then a carbon, and this over here is an alcohol group. Okay, so what is the name of this Aldo pentose? Well, this is what's known as D-arabinose. Okay, so D-arabinose. Right, now let's instead add in another carbon and base them on D-friose rather than D-erythrose. Okay, so that means that this carbon's alcohol group will be going into the page away from us rather than out of the page towards us. Okay, and I should also just mention that of course there are L-isomers of ribose and L-isomer of arabinose, where this alcohol group here of the penultimate carbon will be going into the page away from us rather than out of the page towards us. Okay, so they'll be based on L-glyceraldehyde rather than D-glyceraldehyde. Okay, so now let's talk about the molecules that are based on D-friose. Okay, so let's draw their structures. So we'll start here. Okay, so again, here's this backbone. Okay, here is the carbonyl group. Right, now, originally, this is the new carbon we've added in, so we'll originally start off with having the alcohol group coming out of the page towards us, okay, but we can vary that, remember. Now, off this third carbon, we then have the alcohol group going away from us, just as the second carbon's alcohol group was going away from us in D-friose. Okay, so this alcohol group is going away from us. Then, of course, the alcohol group here is coming towards us because everything's based on D-glyceraldehyde that I'm drawing rather than L-glyceraldehyde. And then here's the alcohol group. So, what is the name of this molecule? Well, this is known as D-xylose, okay? And it's another example of an aldo pentose. Right, so there's one final one that we can make, which is a D aldo pentose. Of course, there are 4 other ones that we can make, which are the L aldo pentoses, where we swap this alcohol group from coming out of the page towards us for it going away from us into the page. Okay, but we're not going to draw all those. Right, so we'll draw the final molecule here, like so, with its aldehyde group there. Okay, and of course it's based on D-threose, so this alcohol group goes away from us into the page, and the alcohol group off this penultimate carbon must come out of the page towards us because of course we're based on D-glyceraldehyde. And then we've got our alcohol group there. So in this case, the alcohol group in this new carbon is going to go away from us, into the page, away from us, and this is what's known as D-lysose. D-lysose. Okay, so D-lysose. Right. So we have these 4 D isomers, which are all 5 carbon molecules and are therefore referred to as the aldo pentoses. Okay, right. So we have 4 aldo pentoses: D-ribose, D-arabinose, D-xylose, D-lysose. Okay, and of course you can also have the L isomers of all of these. So you can have L-ribose, L-arabinose, L-xylose, and L-lysose. Right, so we'll call it there for this video, and in the next video what we'll talk about is then how you can make hexoses which are based on these molecules. And for these we'll stop drawing the 3D structures and maybe move on to drawing structures like this so that we can get used to using both structures, because these are the ones that you're going to see when you look at images rather than these nice 3D structures.